Machine learning-based classification of Alzheimer's disease. The goal of our study was to program machine learning models that can accurately diagnose dementia, particularly focusing on individuals who lack access to neuroimaging tools. Most existing machine learning softwares that detect dementia rely on MRI data. However, roughly 90% of the global population does not have adequate access to this technology. Therefore, we used Washington University's OASIS-3 dataset because it has clinical and demographic data. For example, the patient's age or their score on a written dementia test, as opposed to imaging data. This dataset is publicly available. We began by performing listwise deletion, which removed all subjects that had any missing information. Continuing with the preprocessing of the data, we performed an 80-20 train test split. So 80% of the overall data was used for training the models, and 20% of the data was used for testing the models. This resulted in 283 subjects for training and 71 subjects for testing. Next, we scaled the data, which keeps it within a consistent range of values, reducing possible model bias. Continuous data has a range of values that is typically measured with numbers, and this data was scaled to a normal distribution. So the graphs on the left show how age was scaled to a mean of 0, represented by the black dotted line, and a standard deviation of 1, represented by the blue dotted line. Categorical data, on the other hand, is data that is grouped into categories, for example, socioeconomic status, and this was scaled through a min-max scaler with a minimum value of -1 and maximum value of +1. Next, we label encoded, which converted the subject status of having dementia or not having dementia to integers 0 and 1 respectively, and this helps the computer process data. We then programmed a logistic regression model, which calculates the probability that a subject has or does not have dementia, and chooses the group with over 50%, essentially selecting the more likely option. The primary method of analysis for this model was through accuracy and similar scores, as shown in the classification report on the right, though robustness will be explored in a later slide. As shown, the logistic regression model achieved an accuracy of 95.77%. Then we coded neural networks. These rely on cross-entropy loss, which essentially calculates how wrong the model was when tested on the training dataset, and uses that information to update the weights. Then we performed a grid search, which varies several factors as shown on the left, resulting in 36 distinct models. 6 of the highest performing models are displayed in the table. Epochs are the number of times the model passes through the entire training dataset, and batch size determines how much data the model sees at a time. As shown in the grid search, the 3 best performing models use 250 epochs and batch sizes of 5, suggesting that these values are optimal for detecting Alzheimer's disease given clinical and demographic data. Across the 36 models, the average score was 96.38%. Both the logistic regression model and neural networks achieved higher accuracies than traditional written Alzheimer's disease tests, like the Mini Mental State Examination and Montreal Cognitive Assessment, which are 81.6% and 94.6% respectively. In order to ensure the robustness of our models, we stratified the train test split, which maintains a balance between the subjects with dementia and without dementia across the training and testing subsets. For example, if 40% of subjects had dementia in the training dataset, then 40% of subjects would have dementia in the testing dataset, and this helped to ensure consistency. The grid search also prevented overfitting by discouraging overdependence on any one particular factor. Lastly, the relationship between training loss and number of epochs was observed to detect potential overfitting. If loss increased as epochs decreased, then overfitting may be occurring. If you remember, training loss indicates how wrong the model was. So if as the model passes through the training data set, it's becoming more wrong, then overfitting may be the cause. Luckily, as shown in the sample graph, this did not occur. Our findings demonstrate that both logistic regression and neural networks are valid methods for Alzheimer's disease detection, as evidenced by their high accuracy rates and robustness. However, the neural networks did perform better overall compared to the logistic regression model. The neural network grid search also revealed the best parameter values for this task, specifically batch sizes of 5 and 250 epochs. Although we sought to reduce dependency on neuroimaging data to accommodate people without access to MRI, some of the factors were derived from MRI, such as the normalized whole brain volume. So future studies should eliminate all use of imaging data to best help these individuals. Additionally, a greater sample size and more subject diversity would add to the generalizability of our results. Thank you so much for listening.